Hello, welcome to another module in this massive open online course. So, we are looking at robust beamforming, and we have also looked at the optimization problem for robust beamforming and the solution, the structure of the solution, although we could not derive it in detail. And what I am going to do in this module is I am going to derive the optimal robust beamformer. As I have already told you, the derivation is slightly involved. So, I advise you that if you are looking, if you are going through this for the first time, and if you are not interested in knowing the intricacies of the derivation, you can skip this module. If you are interested in delving deeper into this, you can follow the derivation and understand how this is the robust beamformer is derived, alright. And I am going to illustrate the step by step procedure to derive this robust beamformer W bar, that is the exact structure of the robust beamformer as well as the procedure to determine the Lagrange multiplier lambda, alright. So, we start with the robust beamforming problem. So, again let us just title this is your robust beamforming minimize W bar transpose R W bar subject to the constraint that norm of P transpose W bar less than or equal to norm of H bar E transpose W bar minus 1. This is our robust beamforming problem. We said this is the quadratic constraint W bar transpose R W bar. Of course, R is a positive semi-definite matrix, is the noise plus interference covariance, correct. It is the n plus I noise plus interference covariance, and this is a conic constraint, norm of P transpose W bar less than or equal to H E bar transpose W bar minus 1. Now, what this implies is first of all, if you look at this implies that if you look at the constraint, that implies that P transpose W bar norm square is less than or equal to H bar E transpose W bar minus 1 square, which you can also say that okay. So, now what we are going to do is so the Lagrangian can be formulated as follows. The Lagrangian can be formulated as follows. So, that will be W bar transpose R W bar plus lambda times, we write the constraint, that is no P transpose W bar square minus H bar E transpose W bar minus 1 whole square. Okay. So, this is the Lagrangian. Lagrangian is obviously a function of, you can write this as a function of f of W bar comma lambda. Okay. So, this is your Lagrangian. Okay. Now, differentiate, take the gradient with respect to W bar. Okay. So, gradient of f with respect to W bar. With respect to W bar, and what this is W bar transpose R W bar. So, this we know this is twice R W bar. Now, even before we take the gradient, let us simplify this further. So, this will be before you take the gradient, let us simplify this a little bit further. So, this will be W bar transpose R W bar plus lambda times. Now, norm of a vector square P transpose W bar square is the transpose of a vector times itself. So, that will be W bar transpose P into P transpose W bar minus square of this quantity. Square of this will be well, it will be H bar transpose E W bar whole square minus 1 plus twice H bar E transpose W bar. Okay. And further, now this H bar E transpose, now this is a scalar quantity H bar E transpose W bar. So, I can write this as W bar transpose H bar E, that is transpose of the vector times itself. So, W bar transpose H bar E times itself, which is again H bar E, or basically you can also say this is the magnitude square of this. Both these quantities are equal. So, I can write this as a scalar quantity. So, I can write it as transpose of the quantity times itself. So, that is W bar transpose H E bar times H E bar transpose W bar. So, this is again equal to, so the objective function again, as I have said, slightly involved, can be simplified as, one has to be careful to write each and every term at every stage. So, W bar transpose P transpose W bar minus W bar transpose H E bar E transpose W bar minus 1 plus 2 H bar E transpose H bar E transpose W bar. Okay. And now what we were going to do, we are going to take the gradient with respect to gradient of the Lagrangian with respect to f, okay, or gradient of the Lagrangian with respect to W bar. And this will be equal to the gradient of Lagrange, where W bar transpose R W bar, you can clearly see this is twice R W bar, we know this, plus lambda 2 P transpose W bar minus twice again W bar transpose H bar E transpose W bar. So, this is minus twice again H bar E transpose W bar minus, of course, when you differentiate minus 1 it will be 0, plus twice C bar transpose W bar, that is C bar, twice H bar E, this equal to 0. And now if you simplify this, so this basically implies, now setting it equal to 0, gradient, alright, considering the gradient of the Lagrangian with respect to W bar, and we are equating this to 0. Now if you solve this thing, this will be twice R W bar, or the factor of 2, this will cancel. So, you can remove this factor of 2. So, this will be R W bar, or R plus lambda P transpose minus H bar E transpose, this whole thing into W bar equals minus H bar E. Okay. And now if you set this matrix as Q, so we have P transpose minus H bar E transpose equals Q. So, this implies R plus lambda Q into W bar, I am sorry, there is going to be another factor of lambda over here. So, minus lambda H bar E. So, this is equal to minus lambda H bar E, and this implies that, and therefore, that gives us the equation which is W bar equals R plus, there is going to be a minus lambda times R plus lambda q inverse minus lambda into r plus lambda q inverse into h bar e. This and this you can say this is, therefore, you can write this as star. This is the optimal robust beamformer, which we have already seen. So, this is the formal derivation for that. This is the optimal robust beamformer, all right, and this of course depends on the Lagrange multiplier lambda. And therefore, what we have to do is that we have to determine the Lagrange multiplier lambda to complete this derivation. So, and that is a little bit involved. So, we have to derive the Lagrange multiplier. So, Lagrange multiplier lambda has to be determined. Okay. How to find the Lagrange multiplier lambda? For that, use the constraint. For this, we use the constraint. Okay. And what is the constraint? Remember, our constraint is that norm Pt W bar square minus H bar transpose E into W bar minus 1 whole square equal to 0. This implies that W bar transpose P transpose W bar minus W bar transpose H bar E transpose W bar plus twice H bar E transpose W bar equal to 1. Okay, so basically this is the constraint. Now again you can combine this PP transpose minus H bar E transpose. So what you get is W bar transpose PP transpose minus H bar E transpose W bar. Okay, and this is nothing but our matrix Q that we had seen, plus of course the other terms are there, H bar E transpose W bar equals 1. Okay, this so now you can substitute this. This implies that W bar transpose Q W bar plus twice H bar E transpose W bar equals 1. Okay, very good. Now what we are going to do is we are going to substitute the solution for the optimal beamformer. That is, we have, remember, W bar optimal is minus lambda R plus lambda Q inverse H bar E. Now once you substitute this W, but this value, that is this expression for the optimal beamformer, what you will get is the following expression. You will get lambda square H bar E transpose R plus lambda Q inverse Q R plus lambda Q inverse into H bar B, H bar E. It's a slightly lengthy expression, minus twice lambda. However, you can easily verify it by substituting it. H bar E transpose R plus lambda Q inverse H bar E minus 1. This is equal to 0. Now what we are going to do is we are going to substitute R equals GG transpose. Now, employing this, okay, this is remember R is the noise plus interference covariance matrix. So, GG transpose is a decomposition, all right. Every positive semi-definite matrix, because this is a PSD matrix, okay, this is a covariance matrix. So, this is a PSD matrix. Every PSD matrix can be decomposed as G, some matrix G times G transpose, okay. Now, substituting this above or employing this in the above equation, what we have is this implies gets further involved lambda square h bar E transpose G minus transpose, which means transpose of G inverse. So, you can think of G minus transpose, or there are G transpose inverse or G inverse transpose, both of them are the same, G transpose inverse, okay. G minus transpose I now plus lambda, you can verify this, G inverse Q G minus transpose inverse G inverse times Q G minus transpose I plus lambda G inverse Q G minus transpose inverse G inverse into H bar E, and it continues minus twice lambda H bar E transpose G minus transpose I plus lambda G inverse Q G minus transpose inverse into G inverse into H bar E minus 1 equal to 0. So, this is the equation that you get after you substitute R equal to GG transpose. Now, we are going to do a further substitution, all right, which will simplify this actually, okay, and we are going to see how. So, now we are going to employ a further substitution and the further substitution is, if you look at this matrix, looks like this matrix is the key because this appears repeatedly. So, G inverse Q G minus transpose, we employ its eigenvalue decomposition as follows, that is V gamma V transpose. So, this is basically the eigenvalue decomposition of this matrix G inverse Q G inverse transpose. Okay, so this is the eigenvalue decomposition, and this matrix gamma is the diagonal matrix of eigenvalues. Okay, so this will be gamma 1, gamma 2, so on so forth up to whatever is the dimension, which is gamma L. Okay, so this is a diagonal matrix of eigenvalues. This is the diagonal matrix of eigenvalues, and once you employ this substitution, this implies, so once you employ this substitution, then that is the substitution that we outlined above, G inverse Q G minus or G transpose, G inverse Q G transpose inverse, or G inverse Q G inverse transpose equals V gamma V transpose. This reduces to, well, this reduces to lambda square H bar E transpose G inverse minus transpose V minus transpose I plus lambda gamma inverse times multiplied by gamma I plus lambda gamma inverse V inverse G inverse H bar E minus twice lambda H bar E transpose G inverse transpose V minus transpose I plus lambda gamma inverse into V inverse G inverse H bar E minus 1 equal to 0. Now, this can be simplified as follows. If you look at this vector, we set it as HR. So, we set H bar R. So, set H bar R equals V inverse G inverse H bar E, and this implies, so the equation above reduces to the following: lambda square H bar R transpose I plus lambda gamma inverse gamma I plus lambda gamma inverse H bar R minus twice lambda H bar R transpose I plus lambda gamma inverse H bar R minus 1 equal to 0. And now you can see this is a very simple structure, because if you look at all these matrices, all these are diagonal matrices. So, I plus lambda gamma, if you look at this, this is a diagonal matrix, gamma is a diagonal matrix, this is a diagonal matrix. In fact, its entries will be 1 plus lambda gamma 1, 1 plus lambda gamma 2 and so on. So, all these matrices are diagonal matrices. So, you can basically multiply it out, and you can simplify this, and once you simplify it, the resulting equation that you get will be the following, and you get the final equation for the Lagrange multiplier lambda, and that is given as, interestingly, that is given as this lambda square summation I equal to 1 to L H R. I am going to explain these terms in a minute. So, H R I square, this is the ith component of the vector H I, H R divided by gamma I, 1 plus lambda gamma I, this is 1 plus lambda gamma I square minus twice lambda I equal to 1 to L H R square I divided by 1 plus lambda gamma I. All this 1 plus lambda gamma I terms are coming from the I plus lambda gamma inverse. Okay, you can clearly see that, minus 1 equal to 0, and this is the equation for lambda. Okay, this is the equation. So, you solve this equation, determine lambda. You solve this to determine lambda, and H R I, as I already explained, equals ith element of the vector H bar R, which we defined above. Once you find lambda, so solve this equation, you find lambda, substitute. Now, you have to, once you substitute substitute in basically your earlier equation for the optimal beamformer, which is nothing but W bar star equals minus lambda R plus lambda Q inverse H bar E, and this will give you gives the this. So, this is the optimal beamformer. This is the equation for the optimal beamformer. So, that basically gives the equation for lambda. You substitute this to get the optimal robust beamformer. In fact, this is not just any beamformer, this is the optimal robust beamformer, which is robust to the uncertainty in the channel state information or uncertainty in the knowledge of the channel coefficients or channel vector in the multi antenna system. Alright, so we will stop here and continue with other aspects in the subsequent modules. Thank you very much.